Good afternoon and welcome everybody to this V4SAFETY webinar on the human in simulation. This will be our last webinar in the series of webinars, and we have the following speakers. First of all, my name is Sietse Kaalswaard. I'm the coordinator of V4SAFETY and I work at TNO. The two speakers for the content are Jonas Bergman and Werner Leitgeb. And Jonas, can you give a brief introduction of yourself?
Yes, so my name is Jonas Bergman. I'm a professor at the Chalmers University of Technology. In this project, I've been the project work package lead for the human in simulation.
Thank you, Jonas. And Werner, can you introduce yourself briefly?
Yes, hello everyone. My name is Werner Leitgeb. I'm working at Virtual Vehicle Research in Graz, in Austria. And in V4SAFETY, I was responsible for the task lead of human in-crash modeling that I'm going to present you afterwards. Thank you.
Thank you. Good. Let's continue on and give a little bit of introduction about V4SAFETY. So V4SAFETY is a three-year European project that has been running for the last 3 years and is ending this month. It's on safety and the safety evaluation of vulnerable road users. And I see there is a chat message. Let me check. No. So the project deals in particular with prospective safety assessment, which means what would happen to safety if I introduce a certain safety measure. So we work on or aim for a transparent simulation-based framework, really making simulation more reliable and credible and transparent so that it can be used for prospective safety assessment for various measures. So we're looking at in vehicle, so what can I change to a car or a truck to make vulnerable road users more safe? But it can also be infrastructure, so for example, changing something to a pedestrian crossing, or behavioral. So this might be either in the, for example, in the driving license training, or in things like a maximum speed at some location. So reliability and acceptance of simulation is an important thing for V4SAFETY. So this brings us to our objectives. We want to deliver a framework for road safety and for predictive safety assessment. This includes behavior models, and that's what we will talk about today. It also includes a methodology for baseline generation. So this is what do I compare my new safety measure to? And it talks about models of safety measures. This has been demonstrated in over 10 use cases, and also with a projection over time and a extrapolation across regions, because your analysis may be focused on a certain time and region, and what does this then mean for other regions or 5 years ahead? The project is tightly linked to standardization, so there is an ISO working group that many of our partners are member of, and there is a peers network of volunteers that works on prospective safety assessment and pre-harmonization or pre-standardization. These are the partners of V4SAFETY. It's a sizable consortium, and it's also not a very large EU project, but it actually makes it possible to work very efficiently together and be very effective in results. So if we look at the webinars, you see that this is the last one of 5. The recordings will all be published on our website, and so you can look back at them. Also, this one will become available in, say, 1 or 2 weeks. So that's a whole set of them. And at the end of the webinar, we'll also show where you can find all the results of the V4SAFETY project. So there is plenty of material. As a point of order, you will have a chance to raise questions. You can already put them in the chat if you like. We have a Q&A session at 2 spots in the webinar. So we welcome any questions of you. Then I hand over to Johannes Bergman, and he will tell you about the human in simulation. Thank you.
Yes, thank you. So about the human in simulation, just a second. If we look at where we are in the overall structure of V4SAFETY, this is a picture that's been shown in several of the other webinars, and the focus here is primarily on select models, but also in prepare data and configure simulation, because that's where the in-crash and behavior models do fit in. It's also to some extent a little bit on the right side, and especially on the validation part here. But this shows you where we fit in. And there are 2 different types of humans in the simulations, or human aspects in the simulations that we are considering. One is behavior models, and the other one is in-crash models. And in the project, we have focused on providing recommendations related to the selection, development, validation, and use of behavior models for prospective safety assessments. And for the in-crash models, we should also say that in terms of the budget and the total amount of hours available for this, the behavior part has been much larger than the in-crash part. But for the in-crash, we have we provide an overview of model types and recommendations, and then across different types of virtual entities. One important part that we want to emphasize here is the evaluation scope, and you may not have seen that up in the overall structure, but the evaluation scope really sets and makes clear what the needs and expectations are for a specific assessment. It's what do you want to assess, under which conditions, what do you want to assess on? Is it on crashes or injuries, or what type of injuries and so forth? It's also to raise awareness of choices and how they do affect the validity and accuracy and robustness of the assessment, and to make informed, deliberate decisions early on. So you produce evaluation scope to be able to do these decisions, make them, and document them. And the documentation here is important so that you show and are transparent about assumptions and limitations in, for example, in this case, the models. So now about the human behavior models, we start with agenda. We will cover baseline approaches and the use of behavior models, something about model categorization, the evaluation scope, and the challenges and recommendations. That's primarily related to the deliverable. Then we've also done a literature review, and then some driving simulator studies and open source models and data that are available from the project. And finally, some conclusions. So starting with the baseline, Sitze mentioned the baseline is what you compare to, and In V4Safety, as in this ISO, we define it as in 3 different types of baseline approaches. A is when you have the original case, so that is a real-world case with time series data, and you can replay that with and without the simulation. You don't do any modifications. We have very few model case or behavior models in there, except for when you're adding the system and you want to assess the system. There may be some modeling. For B, then you have an original case. It could be that you have data from crash reconstructions, and you're replacing the behavior of at least one of the participants, the road users in that simulation with a behavior model. And then the last one is synthetically generated cases, where there is no individual case that you can relate it back to, but the cases are generated by stochastic modeling, for example, then of initial conditions or trajectories. And also here you can replace one or all of the road users with behavior models. So then in this project we also have several other layers, but I won't talk about them now. That can go for you can go to the other deliverables for that. And the really important part here is that what we are focusing on is impact assessment, which means that we need to talk about representativeness. We need to consider representativeness. And what I mean then is that, for example, the baseline generation models, they need to generate representative cases matching the evaluation scope. So, for example, when it comes to behaviors, if we are to generate representative crashes, then we need to consider the different crash causation mechanisms that are out there. They could be simplified as reaction times and so forth, but they need to be captured there. Otherwise, you won't capture the representative. You won't be representative of the real world. Of course, then you also need to be representative and model the realistic behaviors such as steering and braking. And other aspects of driving. When it comes to representativeness of outcome, that is the result of the assessment. So when we are talking about safety impact assessment, you will have to define what are you assessing on. Is it time to collisions? Is it reduction in time to collision, or reduction in frequency, crash frequency, or reduction in relative speed of impact, or fatalities or injuries in a certain level? That needs to be decided upfront, and that's also what we talk about representativeness. You need to be able to generate and validate on the metric that you want to assess. So if you want to assess on injuries, you should also validate on that. I'm now going to show 2 different examples of these model uses in the 2 different types of baseline. One is then where we have a set of crashes. Let's say we have hundreds of time series kinematics. We have a model of the driver behavior. So we model why crashes happen. It could be how drivers are looking or are being distracted, or it can just be a reaction time. And then we model also, the model includes when the driver starts braking or steering, and then how the driver brakes and steer. And then we run virtual simulations, and we get to some kind of outcome. And the outcome here is what we're actually assessing the system on: injury risk, delta V, crash, no crash, time collision, and so forth. When we're running the treatment simulation, that means that we are adding the system that we want to assess. Here as an example for collision warning. Then it's how and when do the drivers react to the warning, and how do they brake or steer to that warning. And with that information, the treatment, we can then compare with and without that safety measure, proportion of avoided crashes, differences in impact speed, and so forth. The C case is very similar, where we have stochastic initial conditions, and these stochastic initial conditions could be parameters and distributions of some part of the model, or it could be something else. And here you could also think of it as including, or you can include everyday driving. So for example, traffic simulations where you have all the road users implemented and driving, then they're then a model of the driver behavior in all of the driver or road user behavior in all of the agents. And then again, we do the simulations and we get outcome metrics. We apply the system and we assess the system and we compare in the same thing. So that gives a background on where it's used. Now, I'm coming to what a part that we have identified as important because it makes users, and we see that it could make users and developers of such models think through all the different implications for safety impact assessment. And if you're looking at traditional categorization, you can talk about data-driven or mechanistic or rule-based. You can talk about paradigm-based, such as neuroscience or control theory-based. And then, but what we are proposing is a new model categorization to support users and developers in considering all relevant aspects of modeling specific to safety assessments. And what we're pushing for is to use this as a way to talk about the models. Are you capturing these different components, these different model types in your assessments? And we do this to facilitate accurate, robust, and transparent safety impact assessments. And this is how it looks. We have the first is everyday traffic interaction models. These are models that describe normal routine driving. So driving, how you're keeping lane, how you speed, your speed, your lane, how you're making lane changes, and so forth. So everything that has to do with how you drive in routine driving. But it's not about crash causation and causing of crashes. And this is typically what you would find if you look at traditional traffic simulations, looking at traffic flow and such things. But then we have something called behavior-related crash causation models. And these are specifically when you consider what are the crash causes for a particular scenario, and that you're capturing those in a model. That could be glass behavior, it could be sleepiness, it could be looking at the wrong play, or it could be all of the different types of causation mechanisms that are out there. You can either model them very specifically or do it quite generally by saying there are reaction times, for example, every reaction time delays due to distraction. Then we have something called critical event response models, or CERMs. And these models, they are describing how drivers respond to critical situations. And they're often different from everyday traffic interaction models in the sense that in ETIMs, they are much more satisfying. You're keeping the distance that you feel like. It's not optimal. You're going to stay and drive normally. But in critical event response models, it's much more common to be more open loop, and but also it's really about how you're responding to the critical situation. And of course, then the critical event is how you respond to behavior-related crash causation. The last type of model is what we call models of responses and adaptations to safety measures. And this is then models such as forward collision warning models. How does the driver respond to forward collision warning? But it's also how the driver adapts to the introduction of higher levels of automation, such as over-trust and over-reliance. So this is what we're proposing is going to be following us through the rest of the presentation. If we're talking about the evaluation scope, all the model must be reflected in the evaluation scope. That means that we need to model the different road users as the road users they are. In the V4SAFETY project, we have said that we're always considering a car as the user that in this scenarios. So a car, but it could be conflicting with any other road user. Then we have different safety measures, as was mentioned. We have the in-car, we have infrastructure, and behavior, which could include policy making. And when it then comes to making sure that these models work, what we're saying is that baseline validation is by far the most important, in the sense that it takes all the different models, if you have different models, and it assesses it on the evaluation metrics that you actually want to assess on. And here it's important then that you consider if it's time to collision, if it's crash frequency, relative speed at impact, or fatalities or injuries there. And here you should make sure that you know what you want to create your model to represent. In the deliverable specifically, we have focused on challenges and recommendations. We've done that for model selection, model development, model application, and model validation. And in there, the challenges, that is for about identifying the modeling challenges related to prospective safety assessments. And for the recommendations, it's recommendations that can guide to try to address those. Of course, there's going to be many of these challenges that there is no easy solution to, but then we're describing also how you should reflect that in documentation, for example, with respect to limitations and assumptions. I'll show you now a couple of challenge examples. One is related to data availability for development validation. Another one is about generated baseline, that it should be valid enough for the evaluation scope. I will show these two separate slides soon, but I also include a couple of more. So capturing required crash causation mechanisms and estimating exposure are other things that are problematic and that do require some consideration. And then there are many more. We have a full deliverable of these, so you're welcome to take a look there. If we take a look at the first challenge, we have data availability, and many of you will recognize the figure to the right, which is the high-risk triangle, where we have fatalities and serious injuries at the top, and then everyday driving and non-crash critical events at the bottom. And the higher up you are, the more serious it is, but it's also the less data you have. So conflicts and crashes are really rare, and if you're looking at what's available out there, you have GIDAS, you have EDR data, there are data such as the SHARP2, which only include primarily low severity crashes, and these type of data are then can be used for modeling. It should, however, be noted that, for example, GIDAS, where you have reconstructions of situations and you don't have the measure data, a problem with using such data is that you would model the models that the reconstructions are based on. So that's you have to be really careful if you would do that, and it's recommended then to go for measure data primarily. Although it can be used for GIDAS data is great for using for validation of outcome. And then if we're looking at everyday routine driving, then we're now at the point that there is coming a lot of drone type data where we're collecting data in different parts of the world with drones, but that is primarily that's maybe tens or a few hundred hours of driving, and although they may include some conflicts, they're not going to be very severe. The last type of data that I'm going to mention today is the driving simulator studies and also other type of control studies, and that's a core part of developing behavior models. But they do complement, they're only complements to the real world data, because if we're talking about representativeness, the representativeness in how often crashes happen of a certain type or certain crash causation, that we can't get to that in the driving simulator. We need some kind of real world data to capture that. And then we have modeling and validation of data. They need to be different, and that's a given, but I just want to remind again. Second, then we have model baseline. Is it really valid enough for the evaluation scope? And of course, then the question comes: what is valid enough? How do you assess what's valid enough? And there is actually quite limited literature on this in the domain of virtual safety assessments. For example, this is a plot from a study. Are these similar enough? The mean seems to be, but it's not necessarily true that they are the same, or they could be considered very similar. There are also very large differences between road users, which include different road users in different countries, different demographics in general, and that has a large impact. So if you're developing a model for one country, it's not at all certain that model will be valid for another country, and that's clear in a lot of the calls that have been out there and are out there, on the EU level, that considering variability is very important. Finally, then, that the validation must be coupled to the evaluation scope, and what I mean then is that validating on time to collision doesn't mean that it's valid for outcomes such as injuries or fatalities. So you need to consider that that limitation. That if you're only validating on a lower severity, you can't say much about higher severity. Then about documentation, it's really crucial for transparency, comparability, and trust. And in V4SAFETY, WebPack 3, we have a lot of recommendations of how to think about or what to do when it comes to documentation for different types of models, what to consider for different model types, for different aspects such as validation and application, model development, and selection. Now to the literature review. In the project, we've done a relatively extensive literature review. We're just about to submit this and make it public as open access preprints. And here, some of the main takeaways is that the model availability is very uneven across the model categories. There are many ETIMs, that's everyday traffic interaction models. There are few, but some CERMs, so the critical event response models, but there are very few BRCCMs, so the crash causation models and models of safety measures. Those that we find are primarily for rear end and rear end collisions. Another one is that there is the availability for across road users. It's also extremely uneven. There are by far the most for car drivers. There are some for vulnerable road user, some vulnerable road user models, and then I also mean models where the driver of the car interacts with vulnerable road users. Those are also quite rare. And finally, safety-related baseline validation is extremely rare. And it's often that validation is done on non-crash metrics, even if you're assessing, if you want to assess on, if your assessment scope is on higher levels of severity. So, for example, injury-related outcome is extremely rare, so that you're validating on estimated injury, as an example, or estimated delta V. So that's extremely rare in literature today. So that was the main part of the method. Now there are a couple of slides about other things we did in the project. One is about the driving simulator studies. We've done 2 studies. One study where we had a two-wheeler, so a motorcycle going straight, and the car turning left across the path. And the way that we set it up was that the driver was turning left, and then suddenly the motorcycle showed up, and we looked at the response times there. Another one was this, where we had a car driving and the pedestrian stepping out behind the car and having different speeds and different configurations, looking at what the response times are for the drivers. In terms of the open source data and models, we developed a forward collision warning driver response model, and we have data from the experiments. And in terms of the data from the experiments, they're available, and there are descriptions of the experiment, and we have the output, we have eye tracker outputs and so forth for each of the drives. And for the FCW, we have a reaction type model, which is based on modeling the brake response time to just trigger an AEB, basically. So we're not going into details exactly of how you're braking. It's just a model for reactions, a very simple model of reactions to the warning based on the literature that we found. And the reason why we did this was that we needed this for the use cases. Finally, as conclusions, the specific model, there are clearly specific model challenges for safety impact assessments, and that's also across the different model types and for the different types or different perspectives of using and validating such models. And there are many behavior models they're lacking behavior models in many of the categories and for many scenarios. So that's we have our work cut out for us for the foreseeable future. And then more focus on validation is needed, not the least on baseline validation. Yes, so that's my last slide.
Thank you, Jonas, for this presentation with a lot of information.
So I could imagine there are some questions, and let's see in the chat. So you're welcome to raise your questions here. In the meantime, when I hear all this as a novice user, if I want to do a safety assessment, where do I start? So can I already find some public models in your review paper, for example, that I can start using?
There are some public models out there, but they're still relatively few. Most of them are described in text in the papers, but not shared as open source. But there are some, there are a few that are available and that can be worked on directly.
Yeah. Okay. And if we look at the crash causation type models, are there any? So you said the rear end collision, that's one that is more frequently covered. Are there any others?
There are, I haven't seen any that are public. There are descriptions of such models in literature, capturing different aspects of cognition, both in terms of distraction and situational awareness and so. But there are very few, or I don't think any that I've seen in open literature for now.
Okay. Yeah. And so that as a user, you would then would you really need to start your own simulation study to build your own drive behavior model? Is that the first thing to do if it's missing?
There's quite a lot of knowledge building. We call it knowledge building literature in our literature review paper. That means that there's a lot of material that can help in designing such models, and they're starting out with understanding what are the causes of crashes for whatever scenario you are going to address, and then you can maybe borrow from other scenario types, but you may need to tweak them, but you really should go back to the basics and at least think through what are the causes that these models are to represent. And you won't be able to do everything, but you can start with the causes. You should capture the causes that captures the 80% of the crashes of the type or something like that.
Okay. Yeah. So and you showed an example of the motorcycle oncoming with the car turning left. So if I now have the same motorcycle turning right and the car turning left, so a slightly different scenario, would that model then still mean anything for the new scenario?
It would mean something, but you would have to validate to that extent that that would work in that scenario. It's not a given that it's going to work. You will have different timings. You will have different timings of when drivers are looking where, and different kinematics in terms of speed and so. So there may be there are going to be differences, but they can surely be inspired from each other.
Okay. So in V4Safety, there is all these models are combined in a simulation structure. So does this mean your behavior model is a real-time model interacting with other models?
So the in the V4Safety framework, we are considering it the two different types of models. We have one that is in simulation, which runs at runtime, and that means that it's actually handling all the driving and or whatever it's supposed to handle. But there are also the pre-simulation models, which can be distributions of reaction times or other things that feed into the model, so that you have something like this driver has a reaction time, a mean reaction time of a certain value, another one has another, so that it's fixed throughout the simulation. So those are different types of models.
Okay. There's a question from the audience. I will read aloud. Can you elaborate on road user behavioral adaptations and to how
to deal with that in modeling?
It is really problematic. There are very, very few models out there that do handle that. When we've talked about it from both from the perspective of how can we actually assess this in a driving simulator, for example, when you have multiple exposures maybe, but you don't get exposure over time in the way that you would in the real world. So that's a real concern, and you may need to get some long-term data to get that. It's difficult for me to speculate on how to get that data in a realistic way, but the adaptation itself, if you're thinking about, for example, driver overtrust in a situation, it could be that we just have to accept that it's going to be very difficult to model that and use just distributions of different drivers. Some drivers do have different reaction times because they're overtrusting or won't react at all, and that we have to deal with it on that level. But it is an unexplored area that is not much out there today.
Okay, then I have one final question. So you mentioned forward collision warning model, which is also available open source. So can we now call this a reference model?
So it's not a reference model because it's not a. It depends on what I mean by reference models. If you're talking about UNEC, they have a certain definition of reference models and so forth. But you can say that it's a reference in the sense that it describes something that you want to compare to. But other than that, it's not really a reference model as many would specify it. It's what we provide are a set of parameter settings from literature that we're trying to encourage people to use, just so that we are a little bit more standardized in the way that we're using it for assessments.
And with standardized, meaning also more comparable?
More comparable in the sense that if people use the same response time model or reaction time models for the collision warning, then we can compare the different implementations, for example. But it is a very simple model in the sense that it doesn't take into account distraction or so. It's just a simple response to the warning with reaction time distributions based on literature.
Yeah. Okay. Thank you.
Okay.
We'll have another Q&A session after the next speaker. And if you have remaining questions for Jonas, you can still put them in the chat. So thanks a lot, Jonas, for your presentation. And then we move to our next speaker, Werner Leitgeb.
Okay. Hello, everyone. Hello, everybody. Thank you, Sitze, for letting us speak here in this webinar. Thanks, Jonas, for setting the stage so nicely. I will talk here today about the in-crash models part of V4SAFETY. In-crash about assessing the safety of vehicle occupants and vulnerable road users. As V4SAFETY is about virtual assessment, this is about simulation models. And I also would like to thank my co-authors here, Jonas Öström-Wobelkas, Johan Nereus from Chalmers University, and Christoph Klein, my direct colleague here. Not so much, and not only for helping prepare this presentation, but especially for having so many great discussions on this topic over the last 3 years. So it was great work here and great discussions. Yeah, I will talk here today about the challenges and recommendations in a V4SAFETY context. And especially the evaluation scope, as V4SAFETY calls it. We're going to talk about the in-crash model categorization. So what kind of models do we have here? Occupants and VRU models, including also full sequence assessment / integrated safety topics here. we have those here, and a little bit about availability, and we'll conclude with topics related to recommendations that we come up with that we would like to present to you, and yeah, you will see what is coming. And finally, I will finish with conclusions then, of course. Okay, first of all, not sure who is in this webinar, but in the V4Safety context, in the general context here, we have on the one side crash test dummies, as they are colloquially known, or ATDs, anthropomorphic test devices. They are designed for specific loading directions. These models are based on their physical counterparts, so mannequins equipped with sensors in outer way proportions representing a human being, but the interiors are made out of metal sensors, plastics, foams, all these kind of things. This on the one hand, and on the other hand, we have human body models that are a little bit more universally applicable and potentially more suitable for complex scenarios. But these human body models are definitely more difficult to develop and computationally demanding and complex in application and assessment here. So on the upper side, you have a typical crash test dummy model here on the left side now. And on the right side, you have a human body model, a representation of a human being with a skeleton, with organs, with flesh, and these kind of things. So different assessment tools here that we're going to talk about mostly here today, just for clarification of terms and definitions. Both are there to represent a human being, but the application and the specifics are different. Okay. Both of them, and this is the differentiating part from what Jonas was talking here about, is for prospective assessment of the safety of vehicle occupants and vulnerable road users in crash type scenarios. So we are talking about in crash, we have a crash, vehicles are deforming, people are getting injured. And this assessment focuses on the effectiveness of any kind of safety measures that we or anyone else is going to introduce, going to put into the vehicle, outside of the vehicle, to reduce injury risk. And yeah, this is the important part. So we have a crash. We are going to deal with people, occupants, humans that are most likely going to get injured, and we want to know to which amount and how to, in the end, find countermeasures for this topic. And in V4Safety, our task was to ideally include those models in the simulation framework, provide links, and see how this best can be done. In this context, was mentioned before already, we're talking about road crash scenarios involving motor vehicles. We're going to talk about mitigation measures as the main evaluation scope within this project. So we want to improve something on vehicle side mostly and see what's the effect on the injury risk of the occupant. And we're talking about a couple of road users. This is mostly all kinds of vehicle occupants here, and our vulnerable / unprotected road users. That means pedestrians, bicyclists, power two-wheelers, and riders of new mobility topics here, new mobility solutions. Think of an e-scooters, stuff like that. What is out of scope of my contribution to this webinar is any kind of crash avoidance measures. So we are talking about, we have a crash. So crash avoidance is not a topic. Mitigation measures might have, but the avoidance itself is not a topic here. We are not talking about single VRU accidents. So a bicyclist crashing into a tree or coming off the road is not a topic here of this talk here today. I'm not going to talk about VRU protective equipment, so helmets, jackets, any kind of stuff like this can be assessed with these tools to some extent, but it's not part of what we are talking here. And I'm not going to talk about component certification. This could again be something like a helmet or a safety vest, but in the vehicle, this would be the instrument panel or these kind of things. So different needs, different tools there. Probably similar simulation methods, but not in scope of V4Safety. Okay, I was talking already a little bit about the evaluation scope and the dependency. Evaluation scope in general, why and what do we actually want to do? What do we want to assess? What answer do we want to, what question do we want to answer with this evaluation study, this V4Safety Assessment Framework? And in our context, this is especially important in respect to kinematics, injury risk, and population specifics here that we have. So clearly state and think about your needs and expectations on the choices that you make in respect to accuracy and validity. This has a big influence then on the results and on the assessment. Make clear decisions and deliberate decisions, and write them down, make everyone who is involved in this study, in this assessment, aware of that. And last but not least, document decisions and assumptions, because all these models do not work without context. You have to know what, why, how, who, and when is going to be assessed. And then only then you can interpret any kind of results with these models. A little bit more in detail with this evaluation scope here. I have to cheat a little bit. In general, in V4Safety, on the very left side, I was stealing and borrowing this slide from one of the first webinars here. About the definition of the safety measure under assessment. And here for our side, for this in-crash models, we have to think about the pre-crash intervention topics here. This might be speed reduction, evasive steering, these kind of things. The restraint characteristics, deployment triggering, could be an airbag triggering time that you're going to change or want to improve, safety belt triggers, pretensioners, these kind of things. Other safety measure deployment times, activation logic that you want to think about what is actually triggering this safety measure, could be the braking, whatever it is. Think about reversibility of these measures. Is this a one-time effect that you can and want to achieve, or is this something that can be repeated or changed, maybe even within the crash sequence again? And also think clearly about the limitations your safety measure might have. If you know the limitations first, it's a lot easier. Select the relevant scenarios. Jonas was talking about scenarios quite a lot, the baseline that you want to compare with, all these kind of things. For our in-crash topic, highly relevant. And just one thing I want to emphasize is if your scenarios are related to standardized testing conditions, standardized testing scenarios from regulation, from homologation, from consumer testing, please use those protocols and use your simulation models in the mind of these things. If not, it will be hard to compare the data with that. So if Euro NCAP suggests to use 4Dummy and look at this and that sensor, then I suggest if your scenario is derived from that or is that, use that. If not, if everything is different, think about the general purpose and usage of results here. Think about who is going to get your results. Stakeholder considerations is what we put here. It's a difference if I'm talking about the in-house project, an in-house evaluation study, or if I'm talking to somebody outside of my organization, for example, or outside of a project. Think about, write down the expected outcome of the assessment, about the effectiveness evaluation. Don't start into the blue. make it clear from the beginning how is effectiveness going to be evaluated here. Is this a topic about product certification or optimization? Are you only looking at a concept to get relative data? Is it going to improve situation in general or something like that? Or do you really want to improve or get your belt system approved for something very specifically? And again here, drawbacks, negative effects of your system, of your evaluation, again, make that clear here. Next topic, set the target region and time. We heard just before that it is a difference on where people are driving. Could be the weather, could be anything for our, or behavior is different in one country to the other, and the study might not be available in the other country. We can easily think about that, but for English models, we have a similar topic here. Which population is going to be affected? We think we are all the same, but we are not. Anthropometry and size weight distributions vary largely over the world, and maybe one size does not fit all for what we want to do here. Expect injury loads. I missed something here. So, expected injury loads on human, etc. What do we want to assess? Is this something that could going to affect the head? Is it something to affect the chest or some other body part? And yeah, think about impact on extrapolation and projection here. What I missed in the population part as well is there an age topic in there? Is there a gender and sex topic in there? Think about that and make it clear, make your model choices clear to that. And last but not least, so I should have moved on here, sorry. And last but not least, establish the evaluation result and metrics. What is it, what you're going to assess? Expected kinematics, injuries, injury risk functions, is it the injury risk reduction? Make that all clear from the very beginning, what you are looking at, and do not think of it as an afterthought. And in this context, also the validation level of your model is of high relevance. Okay, so we learned a little bit about what we all need to think about before starting a simulation study assessment run with increase models, but we do not know everything yet. These increase models, as we human beings, are not standalone. We are not going to hurt ourselves in there. We are interacting with the environment, the occupants, the vulnerabilities, or whoever it is. And this environment, in the end, is the thing that hurts the occupant, hurts the vulnerable road user. This is the seat, the restraint, the airbag, or the vehicle exterior, the bumper, the hood, or whatever you crash into. So this environment is the part that links the injury with the occupant, and this is the direct causation. The accident itself, the loading, is the part that causes it in the long run. I need to get some electricity here. So in order to have an effective simulation with a human, you need not only good models of these humans, but you need at least equally good environment models of your vehicle, of your restraint system, of your seat, of your airbag, because it does not help to have the best document available and then you cheat or put something very simple and not very validated on the other side. So the validation level needs to be on both sides. Within V4Safety, there is a complete work package and tasks on these English models in general, not human, the complete English part here. I would like to refer you to the webinar that Lars Schorius from ZF presented in the webinar on Monday. This will be available soon on the webpage again, and where all the explanations and how our our human in-crash models interact and with the rest of the environment, with the rest of the crash here. And you can also go to the deliverable from work package 5 in this context that is available already on the V4Safety homepage in a preliminary version. Okay, so talking about those things, model characterization, one of the important parts here. I already touched the model population that is going to be represented. Anthropometry considerations will be and are of importance here. It is of importance if the occupants or vulnerable road users are to be assessed. So the model choice depends on that topic. And if you are going to assess a full sequence scenario, meaning you have a pre-crash phase influencing the occupant position state during the crash phase, that would be full sequence assessment or an integrated assessment. And yeah, then we'll talk about the availability and limitations on that. The model population within the world, please zoom in if you want to see a little bit more, is quite large. The average person exists, of course, but no one is a full average person. The solution for that was many years ago already to build percentiles of the population, building crash test dummies and assess with average type people. There is a family of standardized sizes in models. Doesn't really matter if it is on crash test dummies or HPM side. And we usually start with an 50 percentile average, mostly male model in the assessments, and then we have a family going down to small female and children and larger occupants up to a 95% model where you really look into large persons and the effect a large person has on the restraints, or the other way around, if a very small or a very large person is affected differently. Yeah. So standardized models out there are in a certain size and weight range. They come from homologation and regulation type of things and are used in consumer testing. For your specific assessment and evaluation scope, you might want to look at something different and not interested in the typical male average model. You might want to do something else. Please be clear on that. Injury risk and this depend on age, size, weight distributions, sitting height, standing height, all these kind of things. And there are solutions out there, but please be specific when starting assessments in this context. I will start here with the commonly known crash test dummies, or more scientifically anthropometric test devices, or ATDs. So if you follow what these wordings, you know this is typical crash test dummies. Our models that I'm talking here today are representation of physical ATDs. So these physical dummies, crash test dummies, are used in physical crash tests. And for that purpose need to be very durable. They are very expensive. They're equipped with loads of acceleration and motion sensors, deflection, these kind of things, load sensors in there. So they are designed as their physical counterpart would be, also as a model. And for size and design features, these models are usually or mostly designed for a specific loading direction. So you have specific models for front crash, for expected front crashes, and different models or different model families for side crashes, where the loading comes from the side and the sensors does need to be reacting to these loads from the side. Also, the models need to be validated in this direction and durable for these kind of loading directions. Outward, they still look rather similar. These crash test dummies have as an output usually kinematics and mechanical sensor data, acceleration, forces, and deflections. And you derive the expected injury risk through injury risk functions. They are related to injury criterion, and mostly those are based on PHMS testing, so testing with real dead people in controlled, usually medical environment, and so these PHMS are post-mortem human surrogates in case you find this somewhere. So these models and these ATTs are validated against them and representative for the specific load cases. The other topic, the other kind of models that I was talking about before are the so-called human body models. The physical representation of a human body model is you and me and everyone else out there. So there is no physical counterpart apart from the human being itself. These models have a skeletal structure, bones, flesh, tissues, ligaments. They are anatomically correct of a human body part, so there are no sensors, and the body parts are not made of steel and carbon fiber. So it's really a model, a mechanical model of a bony structure or a flesh or tissue model. And because they reflect the human being, they are considered omnidirectional and not loading direction specific. So in theory or generally, they can be assessed in more complex scenarios or scenarios that you do not know where the loading comes from and the amount and the weight of the loading. The outputs of a human body model is again kinematics and mostly material stress and strain. So the same physical injury mechanisms that if you as a human being hurt yourself, your flesh is deflected, your bone breaks or is hurt because of overtension or overstrain, overstress. And again, injury risk is determined through tissue level criteria and the risk curves. So this risk curve topic remains with us here for the assessment as well. Okay, on the low end, you have a human body model in a crash here. Then I was talking already about full sequence simulation topics. The models before, maybe just think back, are really there for in-crash phases. So the in-crash phase, the crash itself, somewhere between 100 and maybe 200 milliseconds, not more. All this effort for this crash part. And if you have a pre-crash safety measure you want to evaluate, or if the pre-crash phase, so that's maybe up to 2 seconds before the crash, has an influence on the occupant, you might need or might want to use models that are capable of doing this part as well. This could be any kind of safety feature that is triggered during the pre-crash phase. And you would possibly usually do that if this output or if this pre-crash action has an influence on the crash phase. Could be the position of the model, could be an active behavior, some bracing against the braking or some bracing against the evasive steering, pre-tensioning of muscles in your body, all these kind of things. If your pre-tension of a seatbelt affects these models as well, then you might need to use full sequence simulation model capables as well. The important part here is finite element crash simulation is usually numerically very intensive, so it takes a lot of time. Also already for our 1 to 200 milliseconds of crash time. If you add to that 500 milliseconds of pre-crash time or up to 2 seconds of pre-crash time, these models need to be especially numerically stable and ideally efficient. If not, your high-performance clusters that you anyways need for these models will get overloaded and you will have to wait for your results quite a lot of time. These models need to be validated for pre-crash, especially if you think about standard crash test dummy, they are not reactive at all. So they would just sit, and in a braking maneuver or in a steering maneuver, they would lean to one side or fall over. This kind of potential hazards are involved there. So you need models that are active or reactive, have some muscle and kinematic, active kinematic features, and of course need to be validated for your scenario here. Braking, steering, lane change maneuvers, automatic lane change maneuvers, all these kind of things. Okay, I just show for sake of more videos and stuff, and for you getting a little bit better understanding, one of the V4SAFETY integrated assessment use cases we had here, where two vehicles crash, and from 80, and one of them detects the oncoming vehicle and automatically brakes, in this case from around 80 kilometers per hour to around 60. So we have a huge reduction of crash speed from this eager vehicle, and the opponent vehicle is traveling in this case in this curvy line here at around 30 kilometers per hour. And in this case, we evaluated a delayed air brake action and have an actively controlled FAMS free model in this pre-crash phase, and then this enables us to get a new or a related position for the in-crash phase afterwards. So this model is cut in the middle so that you can see a little bit the skeleton and see that this is a human body model and not a crash test dummy. A quick split to another topic, vulnerable road users. A little bit more complex, more complicated because of the many variables involved in the non-vehicle occupants and road users out there. There are actually two kind of assessment needs there. For the one you try to or currently impactor models are used. So only a very models and also their physical counterparts in the first place, of course. And they're used to assess the physical and structural performance of parts of the vehicle where the VRU impacts. So this is mostly the bumper and the hood, A-pillar, a screen root, and this kind of places where touching or crashing into would hurt the pedestrian, cyclist, you name it, in a very bad way. And these are mostly done to improve the front crash, the front behavior of the vehicle, so the structural behavior of the vehicle there. These impactors are used mostly in standardized testing, and the impactor location speed is kind of preset. So you are not, you cannot use them in a completely out of a range envelope. And if you do not know where your pedestrian vulnerable road user is going to impact your vehicle, you will have slight issues in applying those impactors correctly. The output is again mechanics-based, just like crash test dummies, sensor data, accelerations, forces, moments, and the assessment is done via injury risk functions here. The most common ones are head form models for adults and children, and leg form models. In this case, the upper leg form here on the lower left, and in this case, an advanced pedestrian leg form impactor, where you can see a part of the hip representation up here, and the blue part being the leg form impactor itself. If you are not so sure where your occupant is going to hit your vehicle and need to be more flexible on that because your pre-crash reaction is not clear, and if you want to get a general feeling about where and how occupants are hurt if you hit them, we recommend to use human body model type of models for this VRU assessment. The standard or the already established injury risk assessment, as I was talking before in human body models, can be used here. Again, make sure that the model you're using is validated for the loads, for the expected loads in this context, and for the expected loading directions. Okay, I'm coming slowly to the end of this in-crash webinar aspects. So I would like to kind of reflect in parts again, and in parts a little bit new, on what you need to consider and criteria for application of these human in-crash models. Think clearly about the evaluation scope and the expected outcome when you want to use a model. Make clear what kind of validation level you need for these models. Is it just a qualitative comparison, or do you need quantifications? Do you need numbers in the end? How strong was the injury? What's the expected injury risk for a very specific load type? Could be accident reconstruction. If you really want to compare that to the real field out there and want to replicate a specific scenario, you might need a fully validated model for this case. And if needed, and will be or is already very much on the cards, the certification level of your model. Do you need that kind of thing? Do you need it for official homologation or consumer testing results and evaluations? Use the model, the right model for that part. I will come back to the certification part on one of the following slides again. That's not all, of course. If you ever used finite element models in any aspect for these human in-crash models, it's even more relevant because you are highly software dependent and might have environment, meaning your vehicle environment, your seatbelt environment, your bumper, whatever it is, needs and limitations when you use this model. And I was saying before already, it does not help to have the best validated, most numerically expensive human body model if your environment does not give a similar level of confidence. And last but not least, model availability is always an issue, or not an issue, depending for whom you ask. There are commercial models available for most of what I was talking here today, but also some open source and kind of free to use models as well lately. In general, crash test dummy models and human body models enable relative comparison and optimization of safety features. So they are designed with that in mind. Models predict the average risk of a certain injury, not necessarily a specific injury with a specific person, a specific time. So it's an average of the human population in a certain range. So any kind of precise and absolute values for a real-world crash might be that the use of these models might be limited. You will not get the full result there. So if a bone broke or not in a certain load case might be a little bit hard to tell. And another very important thing is crash test dummies and human body model generations were not necessarily designed to be comparable, not within each other and certainly not against each other. They were always designed to improve biofidelity and risk assessment capabilities. So keep that in mind if you are using these models, and use the same occupant or road user model for the entire assessment process of your evaluation. Do not mix models. You will not get comparable results there. Only that way, this will allow trends and of safety measures to be identified and the influence of differences in models that way eliminated. So please keep that in mind. Don't mix models in one evaluation set. Then So did I jump too much? Yes. Points to consider regarding model applicability of crash test dummies. As said before, they are designed to represent the physical ATDs. So they are in a similar level of validation and have a very much same injury risk prediction capability as these physical models. The sensor numbers are limited in number, are mounted in specific locations, and are designed for specific loading directions, as mentioned before. That means they are limited in biofidelity and universal applicability, and we recommend to use them specifically for all kinds of standardized and pre-known testing scenarios where you already know what the loading will be, and that you know that these crash test dummies are designed for those parts. So homologation and consumer testing are all thought in this direction. Crash test dummies have been a very, very valuable tools in the last 40 years, and that helped bring down injury levels and fatalities on the roads to a huge amount. If you want, though, or need to be a little bit more universal and do not know a priori what the loading on your occupant would be, we recommend to potentially think about using an HPM as they represent a physical human being there. So you can load them omnidirectional and oblique, like crash scenarios that come from autonomous pre-crash braking, pre-crash and evasive steering kind of scenarios. And the injury assessment is not limited by sensor location or sensor placement or sensor validity ranges, but related to tissue data and tissue numbers here. With human body models, a wide range of realistic postures can be used, and new sitting positions, something like very reclined positions that autonomous vehicles promise to provide. Can be assessed with them in a very reliable way. And another thing, recent work in this field making human body models applicable and used and certified for standard virtual testing is currently very much on the way. So summing up current and future work, please, this is an excerpt, and sorry if we are missing something here in this context. Please visit and look at the OpenVT platform, where, amongst others, a Viva model can be open source Viva model can be found. Human HPM for VT and Euro NCAP virtual testing crashworthiness groups are currently pushing and enabling very much to use virtual testing with human models in the very near future. So Euro NCAP starts with monitoring in 2026 already of using these virtual models in their assessment and for their ratings. I linked here the Euro NCAP part and also the HPM certification procedures and needs and front crash application part here. So for your reference. And for those who happened to be at the COVID conference last week, there was a pre-conference on virtual testing, talking about many of these features as well. In addition to that, I would like to mention the road safety cluster that was established last year, where V4SAFETY is also taking part for disseminating and pushing road safety topics within Europe a little bit more and bring that much more to the front. And two currently running and running into the future EU projects are Improve and Protect Us projects that some of these V4SAFETY partners are participating as well. So keep out watching for news on this topic. It's a very interesting and very important one here. So overall, models of humans in simulation and and human behavior, I'm talking here for Jonas as well, are often crucial and the only way of accurately give prospective safety impact assessment. Lots of work in the last couple of years in bringing these models into more official type assessments, not only for development, but really into consumer testing, rating, and in the long run, it will also be into homologation parts. Modeling of humans are crucial for the development, as I said already, and virtual testing, yes, will enter there soon into the homologation field. And yeah, I would like to finish my presentation here with a always true statement from George Box in this context, that all models are wrong, but some are useful and some are very, very useful. And those human-related behavior and in-crash models are very, very useful to bringing safety levels up, reduce injuries, and increase safety on the way to Vision Zero within the European Union and in the end worldwide traffic. So thanks a lot, and I'm happy to receive your questions.
Werner, thank you for your in-depth overview and of in-crash human body models, of human models. So before we go to the questions to you, there was already a question directly after Jonas' presentation. This was a question: is there a generic simulation-based safety assessment methodology that shows which data models simulation platform to use for each type of assessment? And so I did. Jonas, do you want to react to that?
Yeah, I can just say that the what we have from V4Safety include the processor and things like that that was presented before, that include ways to select what type of in-crash models, for example, and what type of components you need. But at the very end, you need to choose the platform that you're going to run your simulations on. And for the behavior models, there is not something that is plug and play in the sense that you go for this and these are the models that you should have. So it's too complex for that. It's very evaluation scope specific, and the domain of behavior modeling is still at the stage where there isn't a lot out there that is public, and that is a problem.
Yeah. Thank you, Jonas. I also, while Werner was speaking, pre-typed an answer. So in the chat, you will now find a link to the V4Safety website, because if we look wider than the human models, then there's V4Safety provides all kind of tools to at least get a smaller set of models and convert to a set of candidates. So please have a look at these results. And for the pre-crash and the in-crash, there are approaches for the selection described in D5.1. So it's also available on the website. But as Jonas said, for the human models, there is no, you need to consider a lot of the guidelines that we give, but still have to make many choices yourself. Then there's another question in the chat, and this, just a moment. This is read it aloud. For crash tests, test conditions like the occupants and seat positions. So both simulations, crash test dummies and human body models are possible. And the crash databases like GIDAS, they contain, do they contain all the necessary data to allow a human body model simulation of real crashes?
That's a very good question, and thanks for that. That's the actual issue. And during my presentation, I was hinting at least at 2 slides that there is one very important aspect, and this is the environment that we have to think about. So the crash data themselves. So this would be speeds, positions, location, all the physics parameters. Might be, with a little bit of luck, found in all these crash databases. That's not necessarily to be GIDAS, but can be any of them. And we will also know to a certain extent who was sitting in this car, who was injured in this car. What is not that easy to obtain is the specific vehicle environment. So vehicle structure. You probably have pictures of a deformed vehicle in there, but specifics on restraint, seat performance, restraint performance will not be within GIDAS, and you will not have a model if you are not the specific OEM of this in-field use case. You will not have the full data on that. So to some extent, you will reach a level that is very close to what was happening in the field, but you will have always a little bit an issue to fully replicating all details there. So the human model is only part of this, and the complete picture is a little bit more relevant. But to assess the general problem within this that led to this GIDAS to have that led that GIDAS took up this case, quite a lot of will be in there, but no specifics on the vehicle interior. Maybe I can also answer to the question before. At least the human ingress part tried to be model agnostic in our assessment, in our description here. There are, of course, commercial and open source models out there. But while we were doing this project, there's this Euro NCAP certification protocol for example, human body models was not finished yet. That was released very recently. And this is relevant for, again, Euro NCAP load cases, not necessarily for something completely different. So what we describe is model agnostic, and you need some certain knowledge on how to apply these models. Please look at this deliverable where a lot about validation and reasoning, why not. Also morphing of models, getting different populations that you might be interested in, how you can get those and these kind of things.
There was a second part to the question, and this is: will the V4SAFETY project deliver hints on how to improve crash databases so that human body models or real crashes can be
This topic, I would say, is out of scope of V4SAFETY. So real crash data assessment is not really part of that. It is part of the other 2 projects that I was mentioning before. So Improver and Protect Us project, that is, and the other road safety clusters. Other road safety cluster project that are mentioned on the slide before. So this is has a lot to do more with crash data and accident data assessment and what's needed out there. In those 2 projects, we go even a step further and look into hospital data and what road safety victims endure after a crash. So this is definitely going into the long-term consequences part as well.
Yes, and the follow-up to that, as a coordinator in the final project review, we typically also get questions about policy recommendations. So this really hints towards a policy recommendation. What the whole of V4SAFETY is depending on crash data a lot, and so what could be improvements to crash data that would really help the industry and the safety community. So thank you, Werner. I have one last question to you. So you saw, you mentioned validation of the human body models and the crash models. So there is 40 years of history and work in there. So that's quite an established area, I would say. So can the pre-crash people learn something from those approaches?
First of all, of course, everyone can. What those approaches in the in-crash part do is on the virtual side, currently, directly, indirectly, whatever translated, also on NeuroNCAP side in the virtual testing active safety aspects as well. So everything there going into virtual testing and needs and requirements is was never invented by the in-crash people as well. So virtual testing validation has its needs and is currently one of the main drivers behind much of the research work out there in this context. Yes, in-crash modeling, pre-crash modeling pairs is one of the relevant aspects in this context. Of trying to standardize and learn from this for quite some time now. And yeah, for EG, EuroNCAP as a working group on this as well.
Yeah. So Jonas wants to comment on this.
No, I don't think there is. There are absolutely things that we can learn in terms of validation procedures and things like that. But the domains are so different in terms of the details that that is then more on the methodology side.
Okay, clear.
Yep.
Thank you. Then with that, we end the Q&A, and I want to thank you all for joining. This is the last webinar of V4SAFETY, and thank you for joining and for your questions. You see the contact details of the speaker on the slide. And also the link to the V4SAFETY website where you can find all the results, and especially the output page where you can find all the reports and the tools. So thanks again for joining. I hope you enjoyed, and the recording will become available in the coming weeks. And with that, I close the meeting. I want to thank the speakers, Jonas Bergman, Werner Leitgeb, and thanks the organization team. Bye-bye then.